In this video, I want to explore the operation of the solar cell. Now, the key to understanding the silicon solar cell is understanding the p-n junction diode. And the p-n junction diode was presented in previous videos, but let's review the operation at least a little bit to refresh our memories. Now, here I have a lattice of silicon atoms, and down here I also have a lattice. Now, this circle is the nucleus of the silicon atom, and each nucleus is associated with 4 electrons in the outer shell, which I will draw here. Now let's draw another nucleus of a silicon atom with 1, 2, 3, 4 electrons in the outer shell. And I'll draw as if it's sharing with an adjacent atom. Now, there are 2 types of silicon. There's p-type and there's n-type. This region on the top, I want to convert that from intrinsic silicon to a p-type material. And I can do that by what's called doping with a different atom, with an impurity. And in this case, let's dope this with a boron atom. So every so often we're going to have a boron atom in this crystalline structure. Now, the boron atom does not have 4 outer electrons. It only has 3 outer electrons. So let's delete this electron here. Now, this produces what we call a hole. And you can think of a hole as a positive charge. And this hole can actually move around. For example, let's say this electron here moves over to this region, and now we have a hole in this particular region of the silicon. Now, perhaps this electron up here, let me erase this electron. Let's say this electron moves into this location. Now our hole has moved to this location. So this hole can be thought of as a positive charge that can move around in this silicon structure. So let's produce an n-type material for this lower silicon lattice. So here I'm going to dope this lattice with a phosphorus atom. So we'll show that in orange. Now, the phosphorus atom, instead of having 4 outer electrons, it has an extra electron. So it has 5 outer electrons, and I'll show that extra electron here. Now, this extra electron is mobile. It can move around. And so let's consider what happens when we form a p-n junction. We'll take this p material up here and this n material up here, and we'll put them together. So let's show that here. So here we have a p-type material that has an excess of holes, and here we have an n-type material that has extra electrons. It has been doped with phosphorus. This p region has been doped with boron. So what happens is that these holes can diffuse from this p region over into this n region. Now, recall that holes can be thought of as positive charges. So over here we develop positive charges, and some of these electrons from this n region can diffuse over into the p region, and this p region will become negative. Now, the interesting thing that happens is that this charge imbalance produces an electric field that points from the positive to the negative. So here we have an electric field in this region between the P material and the N material. And this region is the key to understanding the operation of the solar cell. Now let's say that we have some light that comes into this P region. And this light can knock one of these electrons out of this bond with a silicon atom, and it can produce a free electron and a free hole. And these electrons and holes can move around. And if, for example, a hole moves over into this region of the electric field, we'll get this hole will be pushed away towards the positive region. But if an electron enters this electric field region from the P region, this electron will be pushed down by this electric field, and it'll be pushed into the N region. And if light hits this N region and again dislodges an electron from this lattice and produces an electron hole pair, some of these holes can wander over into this electric field region, and they'll be propelled by this electric field in this direction. So the holes will be pushed in this direction, and the electrons will be pushed in this direction. And that results in a current flow in our solar cell. So let's add a load to the solar cell. Now the P side of the solar cell is connected to a positive terminal, and the N side is connected to the negative terminal. And if we place, for example, a resistive load across the positive and negative terminal, let's call this R sub L, L being load. And when light hits the P region and N region, and it creates electron hole pairs, and these electron hole pairs wander over into this region where we have this electric field, it produces current that flows through this load resistor. So the holes you can think of as flowing positive current this way, and electrons flow this way. And so we have a net voltage across the cell and current flowing into our load resistor. So let's look at the equivalent circuit for the solar cell. I'm going to turn on some layers here. And this shows the equivalent circuit of the solar cell. This symbol here is the diode symbol. This is the P side of the diode, and this is the N side of the diode. So this part of the diode is this P region. This part of the diode is this N region. Now when light hits this solar cell, we model that by current, which is this current source here. And as the light increases, more and more current flows into this path. Now we have some parasitic resistors. We have R sub S, which is a series resistance, and we have R sub SH, which is a shunt resistance across the diode. Now these parasitic resistors limit the performance of the solar cell. You'd like to have this resistor ideally be 0 ohms, and you'd like to have this resistor be infinite, but that of course does not happen. So let's explore the current voltage relationship of this PN junction, or this solar cell. Now if we don't have any light shining on this diode. We can plot the voltage versus current. We'll say this is ground or 0 volts. So let's plot the voltage at this terminal and the current through the diode that we'll call I. So we'll plot I on this axis, voltage on this axis. And in the case of no light shining on the diode, we have a very small, tiny negative current. And we have 0 current where it crosses the axis. And then as the voltage gets above a certain threshold, we start getting a larger amount of current. Now what happens if we shine light on the silicon diode? So let's look at what happens if we add some light. Now this produces a different curve. The light causes this curve to be shifted down like this. And so at this point we have current flow. We have more or less a constant voltage, and the current drops off to 0 current at this point. Now in solar cell notation, it's common to take this quadrant and redraw it. So let's look at how we can do that. So we can plot current this way. So we'll just invert this axis. We'll call this positive current and this positive voltage. And we'll get this current versus voltage curve for the solar cell. Now, if we decrease the light intensity, this curve will move down. So let's undo that. Now, if we increase the light intensity, this curve will move up. It'll produce more voltage and more current. So the key to the solar cell is that we want to extract power. We want this solar cell to do some useful work. And recall that power is equal to current times voltage. So if we are, say, operating at a point right here on with our solar cell, or in fact, if we're let's consider we're operating right here. At this point, we have no voltage across the solar cell. So we've, in effect, have shorted out the solar cell, and we produce a large current. But since the voltage is 0 in this equation, we don't really get any power, so it doesn't do anything useful. Now let's look at this point over here. At this point, we have no current flowing in the solar cell. So the circuit is open, and we're looking at a high voltage. But since our current is 0, we extract no power, so that's not very useful. But if we can operate over at this point, then the power that we can extract from this cell is the area under this part of the curve. Is this amount of current times this amount of voltage here. But if we can operate the solar cell at a point here, we can extract more power out of the cell. We can extract this area under the curve, and that's our power. Now if we're operating at a point over here, we can extract this amount of power out of the cell, because we have this much current and this much voltage. So if we want to maximize the power that we can extract from this solar cell, we should be operating somewhere up here on the knee, so that we maximize the area here and here. So let's change colors here. And so we want to maximize this particular area. At this point is the maximum power point. And so we would like to always have circuits that operate the solar cell at this point so they can extract the most usable energy or the most power from the solar cell. Now let's look at another aspect of the solar cell. Let's say that this is a symbol for a solar cell, and this is the symbol for another solar cell. And we've connected these two solar cells in series. So each solar cell has a plus terminal and a minus terminal. So in the series case, we've added two solar cells together and we've increased the voltage. So in the series case, if we plot this IV curve, this curve will move this way. And the area under this curve has approximately doubled. So by having two solar cells, we have doubled the power that we can extract from the solar cell. As you can see, the area is approximately doubled. So let me undo this curve here. And let's look at another situation. Let's say that we connect two identical solar cells in parallel in this way. And if we do that, we maintain the same voltage, but we double the current capability of the solar cell. So we end up with a new curve that has a higher current capability, but the same voltage capability here. And if you look at the area under this curve, it has doubled approximately. So by adding two identical solar cells in parallel, we're able to extract twice as much power. Same thing for series. Now one thing, let's go back to this curve. Well, let's redraw that curve. Let's say that we have current versus voltage. And let's change color here. Let's say that our solar cell has this current versus voltage characteristic. Now, recall that in our model of the solar cell, we have a series resistance and a shunt resistance. So let's analyze the effect. Let's analyze the effect of the series resistance. And what happens if, as that series resistance is increased, this curve goes more this way. So we lose some power. The area in the curve here has been decreased. So the solar cell is less capable of delivering power. So let's undo that. Now let's look at the shunt resistance. As this shunt resistance becomes smaller, more current is diverted into the shunt resistance and less power is available for our load resistor out here. So as the shunt resistance, as it becomes smaller, this curve tends to shift this way. And again, the area represents the power that we can extract from the solar cell, and it has been diminished. So let's next do a computer simulation of this solar cell. Let's take this circuit here and do a computer simulation and get a better understanding for how the solar cell works. Here I'm in my LT SPICE program, and I've set up a model, an electrical model for the solar cell. This diode D1 is the PN junction diode, and this current source is a measure of the light intensity that the solar cell receives. So the more light, the greater this current flow in this current source. Now this resistor R1 models the shunt resistance across the diode, and resistor R2 models the series resistance of the solar cell. Now this voltage source V1 is used to measure the current versus voltage characteristic of the solar cell. So let's take a look. Let's do a run here. And let's take a look at this current voltage characteristic of the solar cell. So here we see that we see a current axis. This is the current in a solar cell. We have a maximum current in this particular solar cell of about 100 milliamps. Now this horizontal axis is a measure of voltage across the terminals of the solar cell. And here we have 720 millivolts or 0.72 volts. Here we have 400 millivolts or 0.4 volts. So let's see what happens if we change the value of this series resistor. Let's make it larger and see what happens. So let's go from 1 ohm, let's go to 5 ohms and see what effect that has on the performance of the solar cell. So let's rerun this. We'll see, wow, this slope has changed. So the area under this curve has been diminished. So the solar cell is less capable of delivering energy to this load. So let's change this resistor back. Let's put it back at 1 ohm. Say OK. Let's reset our simulation. So let's see what happens if we change resistor R1. So it's set at 100. Let's change it to 20 ohms and just see the effect that that has on our solar cell performance. So let's resimulate. We see that the slope here has changed. So the current falls off dramatically here. And again, we see that the area under this curve has been diminished. So this resistor R1 becoming smaller has decreased the output of our solar cell. So let's change that back to 100. Okay, and let's reset our simulation to the nominal value. So this gives you some idea of the effect that the parasitic resistors R1 and R2 have on the solar cell performance. And this hole can actually move around. For example, let's say this electron here moves over to this region, and now we have a hole in this particular region of the silicon. Now perhaps this electron up here, let me erase this electron, and down here I also have a lattice. Now this circle is the nucleus of the silicon atom, and each nucleus is associated with 4 electrons in the outer shell, which I will draw here. Now let's draw another nucleus of a silicon atom with 1, 2, 3, 4 electrons in the outer. In this case, let's dope this with a boron atom. So every so often we're going to have a boron atom in this crystalline structure. Now the boron atom does not have 4 outer electrons. It only has 3 outer electrons. So let's delete this electron here. Now this produces what we call a hole. And you can think of a hole as a positive charge or shell. And I'll draw as if it's sharing with an adjacent atom. Now, there are two types of silicon. There's p-type and there's n-type. This region on the top, I want to convert that from intrinsic silicon to a p-type material. And I can do that by what's called doping with a different atom, with an impurity. And in this video, I want to explore the operation of the solar cell. Now, the key to understanding the silicon solar cell is understanding the p-n junction diode. And the p-n junction diode was presented in previous videos, but let's review the operation at least a little bit to refresh our memories. Now, here I have a lattice of silicon atoms